Welcome to an episode of Concentrating on Chromatography. Charles and Rajas, I appreciate you joining me this morning.
Thank you so much for having us over.
Yeah, thank you.
For both of you, I'm really interested to start by learning about your scientific background and how did you each end up focusing on evaporation challenges in your work?
I am a physicist by training, and now I'm doing a PhD in bioengineering. And essentially, this problem actually did not come from me. This came from an undergrad, then high schooler. And the lab in general works on essentially making low cost scientific equipment. That's one sort of angle that our lab focuses on. And the idea is that we want to make science accessible to a lot of people. And one of the focuses, we call it the Frugal Science Academy, is essentially going to high schools and bringing synthetic biology to high schoolers and to make them understand that from the get go, sort of like how computing sort of took off. And essentially, we go and we do this big competition called iGEM. Well, the high schoolers do this big competition called iGEM. It's an international conference. They build they build organisms basically. They make organisms do synthetic biology. Last year, Lambert High School built a test for Lyme disease using synthetic biology, and they're high schoolers. They were on 60 Minutes. I think that's the name of the show. And so essentially, the idea is okay, let's get high schoolers excited about synthetic biology. This is the next big frontier. And one of the issues is that high schools often don't have a lot of lab equipment and they cannot afford like the really fancy stuff that universities can. And so we try and build one by one equipment that's useful to them. And one of the key pieces of equipment there was a lyophilizer. And so, a quick overview on lyophilizers for those who are fresh to it. Essentially, you freeze your sample and then you put a vacuum on it, and that pulls out the solvent, which could be water, it could be something else. But for synthetic biology, the key is that with this technique, you can actually preserve organisms. You can you can store them, and then you can just transport them at room temperature if you want, if you do it correctly. Except, of course, like the standard equipment is like $20,000 plus, and that makes it a little hard for a high school to afford. And so, like, can we make a really affordable version of this? And so, the vision was let's make a frugal lyophilizer. So, the lab has made many different kinds of things, including 10-cent ultracentrifuge that spins at 120,000 RPM, a $1 electroporator, which allows you to put DNA into cells. And so these things normally cost like orders of magnitude more than that. And the idea was, okay, let's make it accessible. And the problem started with how can we make lyophilizers accessible to the general public? And then so we were building that. And the evaporation challenge came from that question.
So for me specifically, this was fairly early into college. I was really frustrated by the fact of how I was working on projects that didn't really seem to go anywhere. And for this specifically, as well as like the ethos of the Frugal Science Academy and the Baumol Lab, really focused on making things that people could use and handle. The fact that it was frugal meant it was something that I could complete or accomplish on my own, and it wasn't a project that was quote unquote going to die in a lab. And that's what kind of drew me to the project in the first place. I think that that was how it kind of got started, and it kept growing from there.
Yeah. Yeah. And he started as a first year undergrad in biomedical engineering, and now he's like he switched to electrical engineering, and yeah, that's
Is it fair to say that the specific frustration was that there wasn't an evaporation tool that was under budget, let's say, that there wasn't anything that could be used for this process at the right price point?
I think so. I think that was one of the main constraints that we saw from the high school perspective. We wanted something that they could afford. But that was the thing that started it off. That yeah.
And I'm interested to hear how you two decided to work together and collaborate on this.
Sure. Charles, you want to go?
Sure. So What actually ended up happening was Saad Bamla, who's currently the PI of the lab. I went in one day to interview him for a completely unrelated project, which was honestly at the time out of the scope of my abilities. And I was just talking to him about what I was doing, and he offhandedly kind of just asked me if I was interested in working in. At the time, we hadn't coined the name for the project, which was Evapinator. Currently, it was kind of just like a small project that a couple high schoolers were working on, and I was just asked if I wanted to work on this for the summer. So like I was just like, okay, right now I don't really have summer plans. This seems like a cool project. I might as well like take some time to work on it. It seems cool. I'm going to learn a lot, and that's how I met Rajas for the first time. I was walking out of the lab, and he kind of was just there, and then we spent a couple hours, like kind of talking about things completely unrelated to the project. I was like pitching things that I had very little idea about. It was a really fun time.
Essentially, I was working with and some other people as well, and they were all high schoolers just turned into undergrads in Georgia Tech, that kind of thing. Like, or they were like that was the sort of group that I was working with, and that was on the direction of the lyophilizer, and we were trying to do this whole vacuum system to make it work, and then the control, the temperature, all of that was a challenge at with trying to go like a sub $500 budget. It was not easy. And then what happened? My thesis project is on building a Raman spectrometer that we plan to use for medical diagnostics. And we were visiting collaborators in Thailand who were using Raman spectroscopy to diagnose tuberculosis. And tuberculosis is a major problem in Thailand, and there's no good test. And we were like, can we find a cheap test that will work accurately in this context to distinguish between active and latent TB? So, a lot of people have latent tuberculosis, like one third of the world has it, but not that many have it actively infecting somebody. And so we want to know it's that we need to that it's active. And so they were developing this test, and the way that they were doing it, they had many different centers that would collect blood samples from patients, and then it had to be transported from those centers to the central station where they had the big, bulky Raman spectrometer, the really expensive, high-tech Raman spectrometer, and so they couldn't just move it around, and so they had to transport it. And along the way, they were using a vacuum, a centrifugal vacuum evaporator, and so that's what they used to dry down their samples. And essentially, the issue that they faced was that they faced two issues. One is that the sample would take a long time to dry. They would have a blood plasma sample, a blood serum sample, and then they would take a long time to dry um, with the vacuum evaporator. The other issue was that it would break, and getting service there would often mean like several months of delay. So it would be like several months in the year it was broken, and that was their experience of this instrument. And so when we went there, and so the Vamla lab basically works on this sort of super low cost technology, and we've built a $1 hearing aid. We said we've built this $1 electroparator, 10 cent centrifuge, and we're like, yeah, this is super interesting for the developing world. um, and uh, and they were like, yeah, why don't you build one of these vacuum evaporators for $1? So so I thought for a moment. I said, okay, I can build it for 10. And at that point, I took that as a challenge. And I came here to the US. And then around about that time, I understood that a vacuum isn't necessary for evaporating stuff. I mean, we dry clothes all the time. We don't need a vacuum. So evaporation does not require this. And so I was like, okay, how can we take this to the logical conclusion? Because if we can avoid the vacuum, we can simplify the system tremendously, make it accessible for somebody who, and we can bring down the cost, we can make it small, we can make it use low power such that it will work off of a battery. That was the vision If you can use it in the middle of a village to transport blood samples, like if you can use it in Thailand to transport blood samples, and it's something that is small and affordable that these people can use, then essentially that unlocks so much potential. And so I was like, okay, how can we create this? How can we make this drying system that doesn't require a vacuum? And that's when Charles came in, and I was super hesitant. I was like, okay, um, I really want to make sure that this guy is going to be able to work on this problem, because it's not it requires a bit of work to understand the physics behind it. And Charles was fantastic. Honestly, I was a little skeptical at first that he would be able to take it, but then he just, like, he understood everything about it. And in 4 months after that challenge, we had a sub $100 prototype that would dry samples 15 times faster than their super big the centrifugal vacuum evaporator. That that was how we met and how we got everything together. And Charles did basically all of the hands-on work. He did all the hands-on work and all of the building and all of that. That was how we met.
Yeah, and to be honest, that was like a crazy summer. It was the first summer that I had started research. For a summer, I had touched a 3D printer or a laser cutter. So for me, it was just a huge new experience. Like not only being able to work on a really cool problem, but being able to do it for the first time ever was like an awesome experience. And I definitely wouldn't have been able to even get my foot into the door with like all of the support that I had from, like Rajas, Saad, and everyone else at the lab.
Yeah, I super appreciate the work that both of you are doing together. It's so cool as a manufacturer at conferences like off air we were talking about PitCon. Any poster I see that starts with an affordable way to do X, which is solving a real problem, major kudos to you guys for the work you've been able to do. And it sounds like you both have skills that really complement the other well, which is definitely critical to a productive partnership. So it seems like you both have your own strengths that really help this project move forward.
Thank you. Yeah, I think that does work in the sense that I get to think about the problem from a sort of core physics perspective, and he gets to build and learn. And I guess that's part of the reason why he switched from biomedical to electrical engineering. I'd love to know how this played a role in your decision, by the way.
Yeah, I started off as a biomedical engineer at Tech, and not to get into the nitty gritty of it, but I hate biomedical engineering as a major and potentially a career choice. And in a sense, I was doing what I thought a biomedical engineer would do, like really working hands on a project. Um, and in a fashion that I never thought I'd really be working on so early into like my career for the most part. Um, and something I slowly started to realize was I was not learning the skills I wanted to learn as being a biomedical engineer. To keep it fairly concise, I'd say the major is both broad and narrow at the same time. It teaches you a lot of very base level skills, and it's only applicable in a very narrow area of expertise, meaning that the skills weren't really transferable to anything else. So I eventually switched to electrical engineer halfway through college while still trying to graduate on time, which is a big struggle. It's still a little bit of a struggle even as I'm approaching graduation. But I'm incredibly happy with the switch. It really gave me the skills and the tool sets and the tenacity to really figure out what I was doing and help me in other areas that I never thought it would help.
From what I heard, it sounded like cost and reliability are the biggest inefficiencies, let's say, with traditional evaporation methods. Is there anything else you would add to that list?
I would say a big part of it, is also time. So, for example, freeze dryers take a really long time to run samples. And if time is a constraint, for example, if you're potentially in the field trying to dry samples, there isn't really an effective alternative currently right now. So if you're freeze drying samples for 12 to 24 hours, you not only have to worry about the time it takes to dry those samples, meaning you can't dry any additional samples, you also have to take into consideration the cost of those operations as well. So, like a big aha moment for us was the fact that not only were we able to dry the samples, the fact that we could dry samples out effectively quickly was also something that was amazing because there isn't, to the best of our knowledge, a field based system that kind of lets you just take something out into the middle of nowhere to dry samples. And this was kind of like an aha moment for us because nothing else in the market could do this. And this was something that we could suddenly accomplish. And even if that wasn't the initial heart of the project, it started to kind of drift in that direction.
And if I may piggyback off of that point, the other aspect is field portability. Being able to just take this and it's a box and it's like it fits in a backpack, and at least it can fit in a backpack. We need to do some more engineering, but it can fit in a backpack. So the portability aspect of it is important. And one other key that came up when we were talking to the doctors was sterility. Now, lyophilizers can be made sterile. It's a lot of work to make them sterile, and it's like between runs and so essentially that was the centrifugal vacuum evaporators are not sterile. They can contaminate across samples. So to add to the so cost, reliability, portability, and sterility. So these were the sort of factors that would make it possible to apply this technology in the field for medical samples. And that was where the evaporator that was the problem that the evaporator tried to solve.
Yeah, I mean, just to jump ahead a little bit, at a high level, do you want to introduce what the Evapinator is, and then we can kind of fill in the blanks around there?
Sure. So for a little bit of context, the name of the project, the Evapinator, came from a Phineas and Ferb episode. It's a show that I watched growing up. He's a mad scientist who makes these kind of evil devices that eventually get defeated by a platypus. But there's this episode called the with a device called the Evapinator, which is what it was built or based off of. So as we kind of discussed earlier, we wanted to be able to dry things quickly and affordably, and a big constraint to that is being able to dry things without a vacuum chamber. And as we kind of hinted at earlier, it's actually fairly simple to be able to dry things without the use of a vacuum. As Raj just kind of pointed out, you can dry clothes without a vacuum. If you think about it, if you have a clothesline outside, there are a couple of parameters that you try to optimize for in order to dry things quickly. You want it not to be super humid. You want to apply some heat from the sun, for example, and you want lots of wind. And if you can optimize for those same parameters in like a smaller system, you can effectively dry out samples as well. So we kind of created a loop that can do all of these things. We have a system to get dry air with a very simple cold trap. And then we have a system that allows us to blow air on the samples and repeat that process until the samples are eventually dry. And that, in a nutshell, is like a very brief summary of the Evapinator. We have some additional factors that allow us to have sample to sample sterility and batch to batch sterility. We have some other samples that lets other features that allows for the system to be low power enough to run off a battery pack and compact enough to fit in a backpack, for example.
If I can add one other feature,
Sure.
sorry, right now we're aiming for 4 1 milliliter samples because that's the kind of scale that would be applicable at a sort of field site. You would not need to do 100 probably at a field site if you have it. I mean, you don't get that many patients in a village. Often, if often the point of care uh, would not even have a full time staff. It would be like open part of the day or part of the week, something like that. So you don't have a lot of samples. You have a few samples, and you want it to work for that kind of scale. That's what we're optimizing for.
And what assumptions about your design make the evaporator function differently than other products on the market? Obviously, you mentioned that the vacuum is a big one. I suppose that one assumption about the market, as you mentioned, is that there's a need to do this work in the field, where I don't think that's really something that's being done with any of the popular evaporation techniques, let's say. Like you mentioned, a centrifugal vacuum evaporator, those are typically large, expensive systems, but they're also capable of concentrating 50 samples at a time, where blowdown can certainly do that amount of samples, or maybe a dozen or two at a time. And then you have rotary units where it's doing one sample at a time. So I think of one of the most unique things about what you're working on is the idea that there's a need to do, like you said, 4 samples in the field for immediate at collection processing.
Yeah, so I guess like what we kind of realized was like, as you said, there are 100 different ways to dry things. And like we were going through the process of trying to figure out, okay, is there already a solution to this problem? And in a sense, there are different solutions to this like diagnostic approach, as we were kind of alluding to earlier. For example, there are these really cool tests that you can do where you can essentially drop a spot of blood on paper and analyze that blood through like mass spec or something later down the line. And the samples are dried on that product and are stable for transport and storage without too big of an issue. There are paper-based assays where with like a drop of blood or urine, you can diagnose a disease fairly easily. But something we quickly realized is a lot of these solutions had limitations. For example, these paper-based tests had limit of detection issues where if not enough of your sample or molecule you were interested in was on that piece of paper, it wouldn't be able to detect it at all. These point of care assays had an issue with sensitivity where if you weren't sick enough, these tests may not be able to detect your disease. And even though they were super convenient, they often weren't the most accurate you could use. So what we realized is there was a specific niche that we could fit that these existing tools and technologies didn't currently solve. And that's kind of how we kind of started to build the parameters for what we needed for our system. We wanted to be able to dry a large enough sample so we didn't run into the same issue of limited detection that a lot of these paper-based assay tests did. But we also wanted to preserve enough of the sample so we didn't run into the sensitivity issues that, for example, a blood spot paper assay would have. And we didn't want to take a super long time or for it to be extremely expensive or energy dependent as most of like commercial systems require. So those all kind of shaped our constraints and requirements that eventually led to the evaporator.
Yeah, and I'd love to hear more about the largest engineering challenges you faced in putting together the bill of materials and really creating a working prototype.
A big central ethos to the project was the fact that we wanted this to be built anywhere by anyone. Um, we didn't want this to have custom parts that could really only be made in a lab with the access to like a big Montgomery machining hall, which is kind of like our local machining hall at Georgia Tech. Like you should be able to build this if you are in India or parts of Africa. So the first thing we really wanted to do was how do we make this device in a fashion where you can make this anywhere in the world? So that was our first constraint. No big, scary custom parts. Our second constraint was cost. We wanted this to be inexpensive enough that you could afford to build this if you needed to. So currently our bill of materials is under $100, and in order to get a good vacuum pump, that's already going to be above $100. So that was another big constraint. The way we solved this was like we specifically chose components that you could find anywhere and kind of were accessible to daily life. So For example, our filter right now is a filter that's used in like vacuum cleaners. Vacuum cleaners have HEPA filters, and we've been able to effectively show that we have good evidence to support the fact that we can provide contamination protection with these simple vacuum cleaners, fat vacuum cleaner HEPA filters, as opposed to, like very expensive medical grade filters. We use like pipette tips, which are disposable to direct airflow. All of our components can kind of be purchased through AliExpress. So we're using computer cooling blocks to cool the air down, a computer cooling fan. So everything are components or parts that you can get anywhere. They're fairly common. And I think that was a really big constraint as we kind of started the project, because we wanted to implement a solution, but we realized we'd have to have a custom part for it. So we had to figure out a way to engineer it with what we could easily use or access around us. That, at least for me, was the big constraint, especially as we began to start on the journey for the Evapinator.
I wanted to give a slightly different perspective on the assumptions that went into the device. So one of the big things was, like you said, the vacuum system. And the other assumption that we made was, yeah, okay, if we can do a few samples. But I think the key uh, ideas that allows this is that if you want to do it via sublimation, which is the lyophilize, the freeze dryer approach, we apply a vacuum and then the solvent does not go into liquid phase and directly comes out, and that's needed for a certain class of things that we're trying to dry. But essentially, in the evaporator, we're running the samples, these biological samples, at 40 degrees Celsius, and that's not cold, that's not hot, and that allows us to have a cold trap that doesn't have to be at, say, negative 40 degrees Celsius. So by drying the sample at a basically slight, like at a warm temperature, we're able to have a cold trap that doesn't require as much energy, and that's, I think, another one of the key assumptions as well while building the device. So that, like, the lack of a vacuum and the temperatures that we run at, along with the sample size, all together allow us to make the evaporator small, cheap, portable, and low power. Like all of these things. The other answer to answer the second question, the other engineering challenge, I think, was getting the airflow right. So when we have something like this, like essentially the way that it's very similar in a sense to nitrogen blowdown evaporation. So we like nitrogen blowdown is like nitrogen is like basically dry air as far as we're concerned. It does not react with the sample. In our case, we have air. When we try to make it extremely dry with a cold trap, and we run that over the sample, and that means that we have to get the position, the airflow, we have to account for turbulence. There's like all sorts of issues that we need to solve, which for yeah which if we want to get good airflow on the sample without splattering everything. So that is an important constraint that we face, and throughout, I think that was one of the big challenges, along with the ones that Charles mentioned. That was one of the big engineering challenges in building the laboratory. Yeah.
Yeah, whether it's due to contamination or spillage or no matter what the cause, you can't have samples be destroyed, right? Protect the sample is obviously a good rule of thumb. And certainly, I'll provide materials, anything you'd like to share with the audience. But just to pause for a moment, I suppose it would be good for you to describe possibly what the product looks like, but also just how it operates, if you want to just get into how it works at a very basic level.
So I think a central, like, we want this to be able to be used by anyone. At the end of the day, we hopefully want this to be used by someone who doesn't necessarily need to be a lab tech. So the goal is you have a system where you can put little samples into a box, press a button, and out comes a stable, dry version of the sample that you can transport or use or store or whatever. But we want it to be as simple to use for that process. So the goal of the system is a box and a couple of buttons, and the sample is dry. We're not quite there with our prototyping right now. Right now, we have a version of the system that's kind of a little spread out across the tabletop, tied to acrylic with like a PCB or that we've made, but that is the eventual goal of the product, just a box that anyone can use and take with them wherever they go.
We have some slides on how it works, and if I can screen share. Okay. Perfect. So essentially, the whole constraint that Charles was talking about was, okay, how do we dry this quickly and efficiently? And so essentially, we have the PCR tubes in which centrifuge tubes in which we have the sample. We want to really dry air. And so the question is, okay, how do we create the dry air? And so we have these four tubes in the block. And the way that we create the dry air is very related to something that I think all of us would have seen, which is condensation on, let's say, a cold can of beer or Sprite or whatever you like. So essentially, what happens here is that because this is colder and the air has some moisture in it, when the air cools down, it can't hold on to the moisture and then it deposits it here. And so we exploit this idea, and so we have a cooling block, and then this is made of metal, and this is a thermoelectric cooler, a Peltier unit, and that cools things down. Then when we have humid air coming in, it drops the moisture inside and comes out as dry air. And then essentially we run that in a loop. So the sort of most basic version is we just take air from the outside, we run it through the condenser at, let's say, 10 degrees Celsius, and then we compress that air and then we hit it onto the sample, which is kept somewhat warm. And this basically makes sure that we're not just boiling the sample, we're not destroying the sample. Like you said, keep the sample safe, good rule of thumb. And so this is the most simple version of this that we can have. A slightly more efficient version of this would be to just close that loop so that so we put in all the effort to like remove the moisture from the air. And so if not all the moisture was removed from this, then we run it in a loop. It's more efficient. And then we add filtration, HEPA filtration, as well as an aerosol filter from the pet tips. And that allows us to make sure that there's no contamination. And we have a sterilization system, and that allows us essentially. I think I'm one of the things that I'm really happy about is that we finally figured out how to sterilize the system with ozone, as opposed to the other methods, say ethanol or peroxide or all these things. The constraint is that you have to source it, and it's kind of a bother to source ethanol or peroxide in a field setting. And ozone, you just make ozone out of the air. Like you just take the air in, and you can make ozone with an electric field, and that allows us to sterilize the system. And so that's basically how the system works and sterilizes and prevents batch to batch contamination. In terms of how it prevents sample to sample contamination, essentially we have four pipette tips, and then we essentially have four separate air channels that merge way later. So like four channels, and then the sample goes in there. And so we just have separate air channels that merge way later, and so we can't have contamination coming back. And we HEPA filter the air after it hits here, and that's basically yeah. So that's basically how it works. Uh, if that answers your question.
Yeah, no, that was perfect. I appreciate you sharing the slides to provide that visual element. I'd really love to hear what kinds of samples or solvents you've worked with so far in terms of the prototype.
So essentially, right now, I think the only solvent that we're going to work with is water or something like that. Because if we use any solvent like ethanol or something like that, the way our pumping system works, we're not completely confident that it will not ignite. And so we need to make sure that everything is definitely going to be safe from ignition, which is a major concern. I think that's one of the main advantages of some of the other methods, even the centrifugal vacuum evaporator, which is that it can work with these samples and it doesn't ignite. But at some point, we'll have to look and if our architecture will support. I think our architecture can support working with these other solvents as well. We just have to figure out the right components that work with that. But because this was designed for basically biofluids, we're not aiming immediately for the other solvents. But in principle, the same method should work. Anything that doesn't ignite, which should be fine, and works in this sort of temperature range. If you have to make it very cold, essentially it takes up more power. But it should work for many other solvents as well as, especially for now, we would focus on the ones that don't ignite.
The reason that we're working roughly at 40 degrees Celsius is because it's fever temperature for the body. And primarily because we are working with biofluids, or that is the end goal of the Evapinator, we can work at those higher temperatures without worrying about the degradation of the sample. And you'd be surprised at how much is actually stable in it at those higher temperatures for blood samples, which allows us, as Raj just kind of hinted at earlier, to not have to worry about the power constraints of working at really cold temperatures, such as like lyophilization for sublimation.
Certainly, the in the field operation is a cornerstone of the project and the focus on biofluids. What types of analysis do you think are going to be the strongest or most applicable use cases in terms of you're doing the sample prep in the field? What are the main types of analysis that will come after the Evapinator?
So I think a big part of that kind of depends on like what you're looking for. So for example, if what you're looking for is stable in a dried state, a lot of the traditional analysis that you would run on your sample could also be like you would just have to rehydrate the sample and run whatever traditional tests you'd run. For example, a lot of like plasma based tests have components that are stable in a dried state. A lot of these like ions and proteins are stable. So there isn't much prep that needs to be done as opposed to potentially rehydration or maybe adding a buffer. Now, if what you're looking for isn't necessarily stable or there's some breakdown, it may make sense to eventually run a mass spec, but we're not really there yet with the project per se. We're primarily focusing on things that are more stable in the nature. So it's more of, okay, you can essentially just rehydrate the sample and use it the same way as like a normal sample, perhaps. This could work for any range of biofluids from blood to urine to saliva. Because a lot of what is stable in the sample is also stable in a dried state, which is pretty useful, especially for this application.
And if I can add to that, for with blood, we can't do it with the red blood cells because they will break if we dry them out. So we have to make sure we get the serum or plasma out. So essentially, what we're expecting is that, like he said, most molecules are stable, most metabolites, most proteins, and definitely ions are stable when you dry them out, because a lot of them are done with the dried blood spot paper tests. It's just that you need a mass spec to analyze that generally. And so we're able to do this at much larger volumes, which allows people to use traditional technologies to do the test, in the sense that if you would have done it with in for instance, I think for glucose, one common test is Benedict's test, which is just you literally look at it by eye and you see, okay, how long, like, do I see the red precipitate? And so those are much simpler, cheaper tests that are more widely available in a sort of developing country or like in the field near a village, etc. So if you have the mass spec, then the dried blood spot test works. But if not, so this is sort of volume scale that we can do is corresponds to the volume scale that people usually use. Now, the constraint one the we're yet to test this, so we're basing this off of evidence from dried blood spot, but we're yet to test this. So one difference from dried blood spot is that we're forcing air upon the sample, which means that there's a lot of fresh oxygen available for it, which may cause some degradation of molecules that are very sensitive to oxygen. But we'll have to see. It might be just as good as dried blood spot for those situations, because dried blood spot, you'd have to do it over 12 hours or something like that, or 24 hours, 12, 20, of that kind of time. You leave it overnight to dry. And there's, of course, the paper matrix. That's a constraint that we have to keep in mind uh, for now. Yeah. We have to test it explicitly with these things to be sure.
And we already discussed having a future follow-up conversation, but I'd love to hear the latest and greatest in terms of, I know you're working on doing some publishing, doing some peer review work, so I'd just love to hear where you stand with that.
Sure. If I'm being completely frank, this project is wrapping up at the same time as graduation for me. So things have been a little bit hectic. I think what's really cool about the system right now is we're really close to showing that we're able to have like this true batch to batch and sample to sample sterility, which was something we've been struggling with for a little bit to verify, meaning that you can essentially have all your samples and not have to worry about them contaminating with the ones next to it or with the samples before it. With the ozone system that Raj just kind of mentioned earlier, we don't have any consumables for the cleaning. You kind of just run the ozone for 30 minutes, and then the system is clean and ready to use again, which is great. So that's pretty useful, especially because it really hints at the fact that we may not need any consumables for the system currently right now, as opposed to maybe changing out the pipette tips, which is fairly inexpensive to do, and maybe the HEPA filter every couple of changes. Additionally, we have to verify this, but we have a lot of good evidence to support the fact that we can get samples really dry, the extent of which we're still a little uncertain about. We've been able to get glassy trehalose solutions, which is good enough for a lot of people who are trying to dry trehalose solutions down. We have another partner working out of Georgia Tech, a startup called Eternavax, which is attempting to make room temperature stable mRNA vaccines, which is an amazingly cool project. But a big issue that they were running into was the fact that when they were drying their solutions down in a trehalose based system, it would take them a really long time to dry their samples down. They couldn't use freeze drying, if I remember correctly, because it resulted in bubbles forming in their system, which kind of destroyed the entire purpose of what they were trying to build. So they essentially had a system where they would try to dry their samples out with a combination of desiccants and a flow hood, which took anywhere from, if I remember correctly, 12 to 24 hours to dry their samples out. So being able to do that in roughly like 30 minutes for something that was taking them almost an entire day was pretty cool, because we could see how excited they were about the whole thing. And it was like one of the first times that it was like someone actually using the device. We were able to get samples fairly dry. People are excited about it. I think those are a couple of the really cool things that have happened, at least recently, for the project.
And if I may add on to that, we're doing our best to commercialize this. So we went through CreateX, startup accelerator, and we're trying to figure out, okay, who exactly would benefit the most, what are the applications, and we're seeing significant demand in India because it's a much more cost sensitive market than the US. And of course, all the field applications, etc., sort of spread outness of the system. A lot of those things are much more significant in India than in the US. I mean, in the US also there are remote health centers that are not very well connected, and but I think it's definitely a bigger and more common problem in India, at least as far as I understand. So we're seeing a lot more demand for this kind of technology there. And we're doing our best to make sure it's not just, like he said, a lab prototype, but something that is straightforward to manufacture, straightforward to use, has a good UI. It's not going to be like, okay, you need to do this exactly right, otherwise it's not going to seal. That kind of thing. We're going to make it. We're attempting to solve that set of problems as well, so that it is a viable commercial technology. And again, it's really hard. That's one thing that I realize. I wear this T-shirt when I go to like places where it's like, okay, that was the hardest thing I've done, and I'm doing like that's pretty much one of the hardest things that I've done. And I'm doing my PhD. I'm at the end of my PhD, and this was still really hard because when we're attempting to commercialize, you go through like 100 interviews, and only a few, like a handful, pan out. And so commercializing and making sure that we have an exact product to market fit where some other technology isn't better suited is something that yeah. So we're doing we're also attempting to commercialize. So that's what I'm trying to say.
No, this has been super interesting, and I really appreciate you willing to share with the audience who's very familiar with sample prep, especially in a chromatography mass spec setting, some of the challenges that go into sample drying. So, for Josh and Charles, I really appreciate your time today, and thanks so much for sharing your work with us.
Thank you so much, David. This was wonderful, and it was really fun talking about this. It's been some time since we got to talk about this at length in this way. So thank you so much for the opportunity.
Yeah, it's been a lot of fun. You had great questions.
Yeah, yeah. without a doubt.
Thanks.